Most growing sequences you meet get big in a hurry. Double each time and you rush upward. 1, 2, 4, 8, 16, 32, and 10 steps take you past 1,000. Add the last two together, the way the Fibonacci numbers do, and you still climb briskly at a little over 1.5 times per step. 1, 1, 2, 3, 5, 8, 13, 21. There is another rule, just as simple, that grows far more gently. Its numbers are barely more than 1/3 larger at each step. Watch the size of the jumps as it goes. 1, 1, 1, 2, 2, 3, 4, 5, 7, 9, 12, 16. Slow, patient, almost reluctant. Where doubling has already left the screen, this sequence has only reached 16. And hidden in that gentle climb is a single number that controls the whole thing. Divide any term by the one just before it, and as the sequence runs on, the answer settles onto one fixed value. Not 2, from doubling, not the golden ratio, from Fibonacci. Something quieter and far less famous. 1.324718. This is the story of where that number comes from, and why a spiral of triangles is hiding inside it. The rule behind those numbers is almost nothing at all. Write down 3 ones to start. From there, every new term is a sum of 2 earlier ones, but crucially, not the 2 right in front of you. You reach a little further back, skip the term immediately behind, and add the 2 that sit just before that. In plain words, each new term equals the 1 2 steps back plus the 1 3 steps back. Let us turn the handle. 2 back from the last one is a 1, 3 back is another 1, so the next term is 1 plus 1, which is 2. Then 1 plus 1 is 2 again. Then 2 plus 1 is 3. Then 2 plus 2 is 4. 3 plus 2 is 5. 4 plus 3 is 7. 5 plus 4 is 9. Keep cranking, and the numbers walk upward at their own unhurried pace. 12, 16, 21, 28, 37, 49. That is the entire machine. 3 ones and 1 adding step that reaches back just one place further than you might expect. It is called the Padovan sequence, named for an architect who traced this pattern through the proportions of buildings. Nothing about the rule looks remarkable. The surprise is in exactly how slowly it grows, and the precise number that sets its pace. To measure how fast any sequence grows, you look at the ratio between neighbors, each term divided by the one before it. For Fibonacci, that ratio marches smoothly up toward the golden ratio, 1.618, and stays there. For Padovan, the ratios are more restless at the start. 2 divided by 1 is 2. 4 divided by 3 is 1.33. 9 divided by 7 is 1.29. 21 divided by 16 is 1.31. The answers overshoot, then undershoot, then overshoot again, closing in on their target from both sides. By the time you reach 265 divided by 200, the ratio is 1.325. A few steps later, 616 over 465 gives 1.3247. The zigzag has almost completely collapsed onto a single horizontal line, and that line sits at 1.324718. The gentle growth had a precise speed limit built into it all along, and now we can see it. That limiting ratio is not a rounded off accident. It is an exact number, and it satisfies one remarkably clean equation. Here is where it comes from. Suppose the ratio between neighbors really does settle to some value. Call it rho. Then far out in the sequence, each term is very nearly rho times the one before it, and the one before that is rho times smaller again. Feed that into the rule. A term is the sum of the 1 2 back and the 1 3 back. And after dividing everything through by the smallest, the rule turns into a statement about rho by itself. Rho cubed equals rho plus 1. This cubic has exactly one real solution. Its value is 1.324718, and on forever. Cube that number and you get 2.324718, precisely itself, plus 1. It is called the plastic number, named in 1928 by a Dutch monk and architect, Hans van der Laan, who used it as an ideal proportion for design, the way others reached for the golden ratio. Numbers that grow by a fixed ratio love to become shapes, and the Padovan numbers build one shape especially beautifully. Take equilateral triangles, whose side lengths are the Padovan numbers 1, 1, 1, then 2, 2, 3, 4, 5, 7. Lay them down in order, each new triangle sharing a full edge with the figure already built. Because the rule reaches back exactly the way it does, a new triangle of side 7 fits perfectly against a straight edge that 2 earlier triangles left behind, with no gap and nothing overhanging. The arithmetic guarantees the geometry. Keep adding, and the triangles wind around a center, each a little larger than the last, sweeping out a spiral. This is the Padovan spiral, and it is the plastic number made visible. As you travel outward, the triangles scale up by that same ratio, 1.32, over and over, the growth rate of the sequence written directly into the tiling. If a spiral of shapes growing by a fixed ratio sounds familiar, it should. You have almost certainly seen its more famous sibling. Fibonacci builds its spiral out of squares. The side lengths are the Fibonacci numbers, 1, 1, 2, 3, 5, 8, and each new square fits snugly against the 2 before it, packing into a growing rectangle. As those squares enlarge, they grow by the golden ratio, 1.618. Padovan does the very same thing with a simpler tile and a gentler pace. Triangles instead of squares, and a smaller ratio, 1.3247. So the plastic number is to the triangle what the golden ratio is to the square. The same idea, a sequence, a limiting ratio, a spiral of tiles, running on a gentler engine. 1.32 against 1.62. Over the same number of steps, the square spiral races ahead, while the triangle spiral takes its time. And that difference is exactly the gap between the two constants. The plastic number has one more sequence in its orbit, and it begins from a completely different place. Change only the 3 starting numbers. Instead of 3 ones, begin with 3, then 0, then 2, and apply the exact same rule, each term the sum of the 1, 2 back and the 1, 3 back. You get an entirely different sequence. 3, 0, 2, 3, 2, 5, 5, 7, 10, 12, 17, 22. These are the Perrin numbers, and they hide a famous almost trick for detecting primes. But feed either sequence into that neighbor ratio and you land on the same answer. The Perrin numbers also grow by 1.324718. They have no choice. The limiting ratio depends only on the rule, not on where you start, and both rules are the same cubic wearing different clothes. Rho cubed equals rho plus 1. Same equation, same growth rate. 2 different sequences riding a single engine. The plastic number keeps a strange habit, one it shares with the golden ratio, and it is the reason mathematicians single it out. Raise the plastic number to higher and higher powers, and the results drift toward whole numbers. Rho to the 10th is about 16.6. Rho to the 12th is 29.2. Rho to the 14th is 51.25. Push the exponent higher, and the fractional part, the little left over past the nearest whole number, keeps trying to shrink away. The powers cling more and more tightly to the integers, and those nearest integers are in fact the Perrin numbers again. A number larger than 1 whose powers behave this way is called a Pisot number. There are infinitely many of them, but there is a smallest one, the one sitting closest to just barely above 1, and it is exactly this. 1.324718 is the smallest Pisot number that exists. The quiet growth rate of a slow little sequence turns out to sit at the very floor of a celebrated family. So the Padovan sequence, which looked like the slowest and least dramatic rule you could write down, quietly hides a genuine constant of mathematics. There is a loose hierarchy here. The square root of 2, 1.41, governs doubling and the folding of paper. The golden ratio, 1.62, governs Fibonacci and its squares. And a little below both of them sits the plastic number, 1.32, governing Padovan, Perrin, and a spiral of triangles. 3 simple constants, each the growth rate of an adding rule, each the single real root of its own small equation. The golden ratio gets the posters and the perfume ads. The plastic number gets a spiral of triangles and a place at the bottom of the Pisot numbers, and it seems perfectly content there. It is the same trick played more softly. Start with almost nothing, add back what came before, and watch a fixed ratio assemble itself out of plain arithmetic. 1.324718, the sequence that grows at exactly that rate, and nothing faster.